Hello, so today we are going to take a look at this problem called count univalue trees. So the problem basically is we wanna, when we have a tree, we wanna count how many subtrees are have the property that they are univalue. And what does that mean? So basically a tree or a subtree is considered univalue if all the nodes, its node value and the nodes under it have the same value. Essentially, let me give an example. So if we have, so for example, this subtree is univalue because there is only one for every node here. This one is not, okay? Because there is this 2 value here. This one is not either, because the values are different. This one either is not also because the values are different. But you can notice here every leaf node is a univalue tree. So for example, this one is a univalue subtree, this one is a univalue subtree, this one is a univalue subtree. So this is what we are looking for. Now let's see how we can, so let's take a little bit of a bigger example and count how many univalue subtrees we have. So one thing I want to change in the title here is that, let's say it's subtree, right? Now if we have, let's say, this tree here with 0, and then we have, let's say, 1, and then we have 1 here, and 1 here, and we have 0. So how many subtrees do we have? So as I said, the leaf nodes are univalue subtree because there is only one value, and the leaf node is a subtree, right? So we have this one, we have this one, we have this one, right? And also we have this subtree here because these 3 nodes have value 1, but 0 here, the root here, if we try to get the entire tree, the values are different. We have 0 and 1, so that one doesn't count. So how many we have here? So we have this one, the blue one's the leaf node, we have 3 of them, and then we have the green one, so we have 4. So this is what the result should be. Now how can we determine like that a subtree is a univalue? So already we know that if the node doesn't have a left and a right, then we could, because we know that if it's a leaf node, it's a univalue tree. So one thing we know is that if a node doesn't have a left or a right, both left and right children, then by itself it's a univalue subtree. So if we solve this problem with recursion, we can have our base case, right? Our base case can be just if not node left, which means it doesn't have a left child, and not node right, then immediately we can return 1 as the count of univalue subtrees, right? Now, is that enough? Like, for example, if I'm looking at this here, the value that this node here should return in the recursion to the parent, well, it should say 3, right? Because there are the 2 nodes here, the leaves. These are univalue subtrees, and then there is the subtree that the element is root of it, so it should return to a 3. Which means it should account for the values of its children, but it should also account for, like, it should tell me if it's part of a univalue subtree, right? What do I mean by that? So here, okay, let's first focus on this green subtree here. How can we know that we should count it? So we know that here what we can do is check the node value if it's equal to the value on the left and the value on the right, and both subtree are univalue subtrees, which means basically that their value is the same as all the node under them, then I can know that the entire tree is a unitary value. Let me take a counter example. If you have something like this, and you have something like this, and then you have 2 here, and then you have 1 here, well, the tree starting at this one here, it's not a univalue subtree because of this 2 here, right? So this node here needs to tell its parent that it's not part of a univalue subtree, right? Because if it was, then okay. If it was, let's say, like this, then the parent can say, okay, this entire tree is a univalue subtree. So what I'm trying to say here is that a node needs to tell to its parent two things. It needs to tell it how many, like the count, how many univalue subtrees are under it. In this case, it should just say 1 because there is just this one. But it should also tell it whether it itself is part of a univalue subtree or not, because if it is, like in this case, then the parent can just check, am I equal to this one and this one? If I'm equal to both, then I can consider the entire thing a univalue subtree, because I know that my child here is a part of a univalue subtree, so I know that anything under it has the same value, right? But if it's not, like in this case, I should tell my parent so that my parent doesn't just assume because I have the same value as him that my children also have the same value, right? So it should tell me false here. But in this case, it should tell me the count. So in this case, the child, which is just this one, need to say again both the count and true, because it's the root of the univalue subtree under it, right? And so here we can already know what our recursion should return as a response, right? So basically, when you are doing recursion, especially on a tree like this, you need to know a couple of things, right? You need to know, okay, what are the you have the tools that you have in your disposal is what the arguments you pass to the recursive function, the return, the values that you are going to return, and then reuse by each caller will reuse, right? And then you also need to know, especially for trees, the order that you are going to process thing in. So basically, whether it's, are you going to do pre-order, like process the root node first, and then the left child and then the right child, or are you going to do in order, which is left root right, or are you going to do post order? So these are the most important things when you are doing something like this, a recursive function or a depth first search on a tree, right? So if we kind of try to formalize this a little bit more, let's okay, so another base case that we can handle here is that if that we can handle even before this one is that if the node is null, right? Let's say we got passed null, for example, or we went after the, just to save us in case we got passed null. So if not node, we can just return as the count 0 and say false, right? There is, sorry, say true, because by default it's a univalue, it has nothing, so nothing same as nothing, right? So we could just return true here. Now, what are the recursive calls, right? So naturally for a tree, it's just left and right, recurs on the left side, recurs on the right side. Okay, so now what is the so subproblems here for us, since we are doing recursion, let's just call them out. So subproblems are just calling, let's call it helper, let's call our recursive function helper. So it would be on node.left and helper on node.right. Now the other thing is, what are the arguments that we should be returning, that we should be passing? Well, in this case, you can see we just need to pass the nodes, right? So no big deal, just pass the node. But what should be the return value? Well, as we said, the parent needs to know the count for the left subtree, but it also needs to know if the element, just the child that it's calling, whether it's a part of a univalue subtree or not, right? So it needs both the count and whether it says is univalue or not. And that's what I'm returning here. With this not node, it's 0, the count, it has nothing, no univalue subtree under it, but by default empty set, we can just choose that it's true. Now if it's a leaf, right, we said that for every leaf it's a univalue subtree, right, because it's just one element, it has the same value, so we should return true here. And so for the node left and right, we should return these two values. So if I just put them here, so when we call the helper function, which is our recursive function, we should get left count, because we get count and we get whether it's a univalue and whether the left subtree is univalue. So let's just call that is left univalue, is the left subtree a univalue tree, and that we get by calling helper with node.left, and we get the same thing with node.right. So we'd have right count and we would get is right univalue, and this would be on helper for node.right. Okay, so now that we have this, what should be the order that we did here? The other part of what we should find for the tree here. What order are we going to do the recursion? Are we going to process it in a pre-order, in order, or post-order? So in order to know whether a root constitutes a univalue subtree with all its children, we need to know whether its left side is a univalue subtree and whether its right side is a univalue subtree, which means that we need to have already processed all of its children, right? Which means we can't process it first, right? So this one, we can't use this one. We can't process it in order, because in order we would mean left, then root, then right. Which means right, which is the child here, would be processed last. And so we will process root without knowing the result of its right child. We can't do that, right? Pre-order is root first and then children after that, and that doesn't help us because we need to know the values for the children. But post-order does left, right, then the root. So it does both children, subtrees, and then the root. So this is what we want, post-order, okay? Which means we will call the recursive functions, then do our processing for the root. So this is the processing for the left, for the right, then we do processing for the root, right? So how, or the node in our case here, because the helper function would be called, so it would be called like this, helper with node. Okay, now for the root node, what should we do? Well, if the left subtree is not a univalue subtree or the right subtree is not a univalue subtree, we should just return false. So let's first just separately handle the case that we might have a univalue subtree, because the left subtree is a univalue subtree and the right subtree is a univalue subtree. So if this is the case, then we will do a processing here. But if this is not the case, that means that this node cannot be, so basically maybe something like this. This node cannot have a univalue subtree, so we can just right away return what should be the count. So the count is whatever count of the left child and the right child, right? We don't add anything because this root node here doesn't, so maybe we have a subtree here, maybe we have a subtree here, but we don't add anything because this one here doesn't give us a new univalue subtree because of this 2 value here. So we should just return left count plus right count, and we should say false because this tree here doesn't constitute a univalue tree, right? So we should return false. Now, if both are univalue trees, so maybe one here and one here, then we should add 1, but only if this value is equal to both. If this was 2, then this is not a univalue tree, so we need to check that. And so we need to make sure that so here we check if there is even a node.left, which means not, so what we need to do is if node.left, so we should check if node.left, so if there is a left child and so if there is a left child and so if there is a left child and the node.left value is different than the node value, what does that mean? So that means we have something like this, 1 and 2 here, and then maybe we have some other value here. We don't care yet, we don't know yet, but even if this value was 1, then this won't be a univalue subtree because these values are different. So we can immediately return the count is still the same, right? We didn't add a new one. But now this tree is not a univalue tree, so we need to return false. And the same thing happens for the right subtree. So, and node right. Val is different than node val. Then at this point, we should return left count, so the same thing plus right count, and false. Now if none of these are true, then that means we have either we are in one of the two cases, either so actually we are in the, because we already handled the case where both are empty, this means that here we have both values, the left value and the right value are equal to the root node value, which means we are in a case like this, okay? Because if any of them wasn't equal to the node value, we would have entered one of these two ifs, so which means that immediately we should add 1, because because this one here is a univalue tree, because the left subtree is a univalue tree, the right subtree is a univalue tree according to these two, and these values are equal, so this entire thing is a univalue tree. So here that means that we need to add 1 because we have a new univalue subtree, because maybe there is another root node here. So left count, or maybe even if it's just the root, this is just the overall tree needs to be counted too, right? So this would mean left count plus right count, and here we should return true, right? Because this is a univalue tree, and that's pretty much it. So one thing you can realize here is that we actually can get by without this base case, because this base case would be supported by this here. Because by default, if we don't have any no nodes, we return true, which means for the leaf nodes, we will get back true for both its left tree and right tree, because those are empty. And so we'll enter this else here, and we'll return 1 plus 0 for both, and true, which will give us the same value here, right? So we could also remove this base case here, but it's just good to do it in the beginning so that you make sure you aren't missing any cases. And here we can just pass to get the final value, the overall count is equal to something here. We don't care at the end about whether the entire tree is univalue or not. And so we call the helper function with the root, and we can just return the count. And this is pretty much it. So let's just run this on an example and see if it works. Okay, so here is an example of what we just saw in the overview. And so here we just do the base cases, right? If there is nothing, we just return 0, and by default it's true. If we are on a leaf node, then we return the count of univalue trees is 1, and we return true. We recurse on the left child and the right child, and we get the two values that the parent needs, which are the number of the subtrees that are univalue under the left node, and the number of subtrees that are that are univalue on the right subtree, and whether this node that left constitute the root of a tree that is univalue, and the same thing for the right child. And if both the left and the right child are part of a univalue subtree, then that means potentially our current node may constitute a univalue tree, right? Maybe a root of a univalue tree. And so we try and see if it is. So if we have a left node and the value is different, that means it isn't, right? Because the value of the node and its left child are different. So in that case, we return the same number of univalue subtrees, and we say false because node.val is not a part of univalue tree. And we do the same thing for the right node. Now, if we exit these two if loops, that means we have the two values are equal, or maybe it doesn't have a left child or it doesn't have a right child, right? So if it doesn't have a left child, but the value of the right value is equal, then that's still a univalue tree. If it doesn't have a right child, but it does have a left child and the values are equal because we exited this if loop, then it's still a univalue tree. And if both it has a left and a right child and both values are equal, which means we didn't enter these ifs, then it's also a univalue tree. So you can see once these two if loops are false, we must have a univalue tree that has as a root this node, right? This node that we are calling a helper with. And so which means that we need to add to the count for both the left child and the right child, we need to add 1 because we have a new univalue tree. And here, sorry, we need to return true, right? Because this is part of a univalue tree, so we should return true. And then now if this is not the case, that means we don't have a the left subtree is not a univalue tree, and the same thing for the right, or the right subtree is not a univalue tree, then that means we don't have a univalue tree at the root node, at this node basically, and so we need to leave the count the same and just return false. And to launch this helper function, this recursive helper function, we need to call it on the root. We are not interested at this point in whether it's a univalue tree, we just want the count, and so we return that. And here I have a tree that is like this, that looks like this, where we have 0 as the root, and then we have 1 here, and then we have 0 here, and then we have 1 as the left child of that 0. So you have 0, and then 1 as its left child, and then that left child has 1 here, and then has 1 as the right child, and then this 0 has 0 as its right child. So you can see we have the leaf nodes 1, 2, 3, 4. So we have 4 univalue trees just from the leaf nodes, but we also have this tree here that is univalue, right? So we have 5, but the rest are not univalue trees, right? So that means that we should. So let's run this and see. So here I have an assertion that asserts that it's equal to 5. So let's just run this and make sure it passes, and it does. So we are good. Now, in terms of time complexity, we will at most go through the entire tree, right? We have to go through the entire tree, right, to count these, right? So what this means is that we have O(n) time, because we don't visit any node twice. We visit each node only once, but we visit all nodes of the tree, right? Now, in terms of space complexity, the main space thing that we are using here is the stack because of the recursive calls here, right? But we go through the left child and we keep going until the end, and then we bubble back up, right? And we do the same thing for the right child. And so at each point, what would be on the stack is just one branch, right? And each branch of the tree is at most the height of the tree. And so in terms of space here, what will be in the stack at any point of running this algorithm here would be of h space, which is basically the number of methods calls that would be on the stack at each call, right? And so h here is just the head of the tree. And that's pretty much it for the time and space complexity for this function. And as I said earlier, actually we can get rid of this base case because it gets handled in this else case here. Because for this here, we would not enter this if loop, we would not enter this if loop, and the left count and right count would be 0 because of this, and so we will end up with 1 and true, which is the same thing we'll end up with here. And so we can just delete this, and this will still pass, right? And yeah, so that's it for this problem. Thanks for watching, and see you on the next